In this lecture video, we're going to talk about collisions, two things hitting one another, and the two different types of collisions that we can have, and whether or not momentum and or energy is conserved in each type of collision. So the two types of collisions that we have are inelastic collisions and elastic collisions. Inelastic collisions, think about two railroad boxcars, one at rest, one moving. They hit each other, couple, and combine and move off together. That is a completely inelastic collision. Sometimes I think of inelastic collisions as sticky collisions. And as we've seen already, momentum is definitely conserved in an inelastic collision. So I'll put a big check mark right there. Elastic collisions are bouncy collisions. So think about two carts with magnets of the same pole facing each other. One cart hits the other one, and the magnets bounce off of each other, so the carts bounce off of each other. And that is called an elastic collision, or think about a bouncy ball. So I think about elastic collisions as bouncy collisions. And momentum is definitely conserved there. In both cases, inelastic or elastic, the only forces acting between the two objects are Newton's third law pairs. Those cancel out. So the net force acting on the system is zero, therefore momentum is conserved. That is excellent. Well, in inelastic collisions, we've also already seen that mechanical energy is not conserved, so that the kinetic energy of one boxcar coming in is not going to equal the total kinetic energy of the two boxcars after the collision. So we're going to put a big red X for inelastic collisions and mechanical energy being conserved. For elastic collisions, think about a perfect bouncy ball. You drop it, it hits the ground, and it comes right back up to where you dropped it from, the same height. There we see energy is conserved, and in a perfectly elastic collision, that is the case. Mechanical energy is conserved. So when I talked about those two carts with magnets on there, then we could compare the kinetic energy of the first cart to the total kinetic energy of both carts after the collision, and it would be conserved. And in fact, that is the way you tell whether or not a collision is elastic or inelastic. You look at whether or not mechanical energy is conserved. If the answer is yes, it is elastic. If the answer is no, I don't care how bouncy or how sticky the collision is, the answer is that it's an inelastic collision. All right? So we're going to take a look at an example of a collision, and the first question we're going to ask is it elastic or inelastic? Okay, so here's our example problem, and we have a blue cart of 1 kilogram moving at 3 meters per second to the right, and we have a stationary red cart of 2 kilograms. Blue cart collides with the red cart. That's what this is. This is the collision, and after the collision, the red cart's moving to the right at a half. First question, what is the velocity of the blue cart as a result of the collision? Now, here's a really, really important thing that you need to keep in mind. We are not told that this collision is elastic. So I cannot assume that this collision is elastic. You will never assume that a collision is elastic unless you are directly told that it is a perfectly elastic collision. Otherwise, the only tool available to you is conservation of momentum. So that's where we start. We know that the initial momentum of the system has to equal the final momentum of the system. Initially, before the collision, the only thing that has momentum is the blue cart. So we've got 1 times 3 is our initial momentum. That's going to equal the final momentum of the system. So both of these carts are moving, we assume. Perhaps the blue cart isn't. We'll see after the collision. So the momentum of the blue cart is going to be 1 times whatever VB is, plus, and it is a plus sign because the red cart is moving to the right, positive momentum, positive velocity, 2 times 0.5. Okay, so remember that momentum is mass, which is 1 for the blue cart, times velocity, which is 3 initially for the blue cart. So mass times velocity. And so now we have everything we need to just solve for the velocity of the blue cart. So we have 3 is equal to VB plus 1. Subtract 1 from both sides, and we get 2 meters per second is the velocity of the blue cart. All right, cool. So we can fill that in. We have 2 meters per second for the velocity of the blue cart. The next question that we're going to ask then is this collision elastic? So the thing that we check for is energy conserved? So let's see here. Is K naught equal to K final? And we'll put a little question mark here. The only thing with kinetic energy initially is the blue cart. So we have half the mass which is 1, times the velocity squared, which is 9. Is that equal to the final kinetic energy? We have half the blue car's mass times its velocity, which is going to be velocity squared, which is 4, plus the kinetic energy of the red car, half of 2 times 0.5 squared, which is 0.25. So we look at the math here. On the left-hand side, we have 9 halves, or 4.5. And is that equal to what we get on the right-hand side? Half of 4 is 2, and half of 2 is 1 times 0.25. We have 0.25. So we only have 2.25 joules of kinetic energy on the right. We have 4.5 joules of kinetic energy on the left. Clearly, energy is not conserved here, so it is an inelastic collision. All right? Even though it's a little bit bouncy, it looks like the red car bounces off the blue car a little bit, I don't care that it's bouncy. If energy is not conserved, it is inelastic. Okay? So let's take a look at a simple equation that can help us out in solving when we know a collision is elastic. All right, so taking a closer look at elastic collisions themselves, like I said before, you cannot ever assume that a collision is elastic. All right, you have to be told directly that it's elastic, or you have to prove using conservation of energy that it is elastic. All right, but if we do know that the collision is elastic, if we were told in a problem that the collision is elastic, then we have a tool at our disposal. We always know that momentum is conserved. All right, so breaking that down, we've got m naught v naught is equal to m final v final. Great. We also know that kinetic energy is conserved. So k naught is going to equal k final. So 1/2 m naught v naught squared would equal 1/2 m final v final squared. Now you can definitely use these two equations to solve your problem. And all of these types of problems are going to end up with two equations, two unknowns. And unfortunately here, the algebra becomes a little bit burdensome. And so what we can do is actually combine these equations, and we can get a simpler equation to use for the conservation of energy side. We're always going to use this equation for the conservation of momentum side. But it can be shown through algebra that in combining these equations and getting rid of some variables, let's say we've got two objects here, and this is where this is going to come into play. If I've got two carts colliding with one another, then we could say that the initial velocity of cart A plus the final velocity of cart A is going to be equal to the initial velocity of cart B plus the final velocity of cart B. And with two objects that are colliding with one another and the collision is elastic, this will hold true. And that is a much simpler relation to use than the above, because it doesn't have squareds in it and you don't have to deal with it. So if the collision is elastic, I highly implore you to use that simplified equation to solve for your unknowns. Two equations, two unknowns is what you will usually end up with. All right? So there it is. To prove a collision is elastic, you have to prove that energy is conserved. Use the kinetic energy equations. If you know the collision is elastic, then you're going to use these equations here to solve for your unknowns. All right? That's it for now. See you next time.